the next couple of days, we are going to be doing everyone's favorite topic, word problems. Okay, not everyone's favorite topic, right? And oh, did I give you an extra one?
No, you go. I see where you got.
All right, everyone's favorite topic, word problems. And before we even get into this topic, I'm going to ask you a question, okay? So let's say it's someone's birthday and you want to get them a balloon. Okay, so you go to the party store and you ask them to fill up a balloon, and they have a little machine there that does it, right? Now a balloon is kind of like a sphere, not really, but we can pretend that it is. So it's going to look like a sphere. And as you fill it up with the machine that's kind of filling it up at a constant rate, the balloon is expanding, right? So we have two things changing as we fill up this balloon. We have the amount of air that's going into it, and then we have the diameter that's expanding. So the things that change is basically the volume of our balloon. So the air going inside of it is changing the volume. And another thing that's changing is the diameter of our balloon, right? So it's getting bigger as we add more air into it. Okay. Which one is easier to measure? The change in the volume or the change in the diameter? I see your diameter. I don't actually know if it's the diameter. Why would it be easy to measure the volume or the change in the volume?
We have the direct iron square.
How am I filling up the balloon? With a machine, right? And the machine has a little thing telling us how fast the air is going in, right? So yeah, it might be kind of easy to measure the change in the diameter, but we actually have a machine that's telling us how much the volume is changing. It's telling us how much air is going in.
What if it doesn't tell you?
Okay, well then it's just a hard question in general, isn't it? Okay, let's assume. Let me draw the little air pump here. There we go. Here we go. Here, and if we zoom in here, there's a little screen on it, and it's like the change in volume is 3, and then we got Jude here looking at it. There we go. All right. Now Jude has seen the change in the volume, and we can all agree that we know, yes, we know how fast that the volume is changing. Okay. So in this scenario that I actually conveniently wrote up here, it's actually easier to measure the change in volume. Yeah, David?
Please tell me this is posted.
Yeah, it'll be posted. All right. He looks so tiny in that picture now that I zoomed out. All right. It's easier to measure the volume. Okay. And it's kind of hard to measure how fast the diameter is changing unless you're like actually measuring the diameter every couple of seconds, right? So that actually wouldn't be very easy. It's also not easy to measure the diameter of a balloon in the first place, right? Because it's kind of hard to measure and hard to handle. Okay, so we know that we can measure the change in volume, and what if we wanted to know the change in diameter? Okay, maybe there's a way to relate the change in volume to the change in diameter over time and use our known change in volume to find the change in diameter. Okay, the whole idea behind this is this concept called related rates, which are basically word problems involving derivatives. Okay. Okay. So related rates in general is when we want to find the change in one thing, if we already know the change in another thing. Okay, maybe we can relate them together and find what the change is. There's a little strategy that I have for this. The first thing I want you to do in any word problem is to draw a diagram, right? Diagrams are always good to draw. So that would be step number 1. Step number 2, since we have a lot of different things changing, we're going to introduce some notation. So maybe like variables that come out, maybe functions of time like volume or speed, something like that. Okay. The third thing we're going to do is we're going to find some sort of way to organize all the information we're given. So we're going to figure out what we're given in the question, and we also want to figure out what we want to find. Okay. Next, we're going to write an equation. So step 4, we're going to find some sort of equation. I'm either going to be given an equation, or I'm going to use something that I know based on the geometry of my diagram. Step 5, we're going to use implicit differentiation. So what we're going to use on our quiz is what we're using here. It's going to look slightly different than what we've done on Wednesday, but I'll explain that a little bit later. Okay, and then we're going to substitute the given information into what I want to figure out what I'm looking to find. Now that was very abstract. If that went over your head, don't worry, because we're going to put this all together in an actual example. Okay, I have a warning here, and I think I want to talk about the warning while we do a question. So let's come back to that warning later. Okay, before we do a question, implicit differentiation is going to look a little bit different than what we've done on Wednesday. And the way it's going to be different is all of the functions I'm going to be using in related rates questions are going to be a function of time. All the questions I'm going to give you are going to change with time. So the variable we're differentiating against is going to be time or t, okay? On Wednesday, I gave you functions that were functions of x. Okay, so we found dx of functions, and that's how implicit differentiation worked. If we're dealing with a derivative with respect to t, we're going to find dt and not dx. Okay, so maybe a good thing for your quiz, what would be the derivative of y squared with respect to t? Sam?
2y dy over dt.
Good, 2y dy dt. Very similar to what we did on our quiz. Something that'll be a little bit different from your quiz, just notation wise, is what happens when we differentiate x cubed with respect to t? What would that look like?
3x squared dx over dt.
Perfect, 3x squared dx over dt. So it looks a little bit different than what we did on the quiz, just because I'm changing what I'm taking the derivative of with respect to. Okay, so I'm not focusing on x anymore. We're focusing on t. Okay, if we're all good on that, let's actually do an example. So if we flip our page over, we have our balloon example that Jude brought his balloon to the party store. Okay, let's say we have a spherical balloon. We're pumping air into this balloon, and we know that the volume is increasing at a rate of 100 cubic centimeters per second. Okay, we want to know how fast the radius of the balloon is increasing at this specific point, at when the diameter is 50 centimeters. Okay, now I kind of gave you an equation here, so you kind of already know where we're going towards. But let's go step by step and see how we can solve this. Okay. Step 1 is to draw a diagram. So step 1, well, a good diagram of a spherical balloon is maybe drawing a sphere, right? So I'm not the best at drawing, but I have this little feature on my iPad that might help me out here. There we go. That was perfect. All on my own. It's cheating, isn't it? Okay, so we got a little balloon. Oh, just messed it up. Okay, and then maybe the back of the balloon looks like this. Okay, so that's my sphere. The radius of the sphere is if I start at the very center of my sphere and go out to any edge, right? So this is my radius, okay? And I know that air is being pumped into it. So I know that air is going into it at a rate of 100 centimeters cubed per second. Okay. Now, I want to know how fast the radius of the balloon is increasing when the diameter is 50 centimeters. Since this is a general diagram, I'm not going to label the radius as 50 centimeters yet, okay? Because that's what I'm interested in at a very specific slice of time. Okay, so this is my diagram. Pretty good. Step number 2 is to introduce some notation, okay? looks like I have my volume of the balloon is what I'm interested in. What sort of variable do you think I should use for volume? V, right? V sounds pretty good. So I'm going to say that V is volume. And then I have the radius of the balloon. What should I use for that? R, good. Okay, now I like to label it out just so I don't get confused in the future. I know in this example, it's pretty easy to figure out what volume and radius are. But let's move on. Okay, so step number 3. Step number 3 says we need to figure out what we're given and we need to write that in terms of derivatives and functions. Okay, so let's just read this question. Air is being pumped into a spherical balloon so that the volume increases at a rate of 100. How can I write that in terms of derivatives? Sam?
Like you want me to find the derivative of?
Well,
Or.
how can I write the volume increases at a rate of 100 in terms of
Oh,
derivatives?
dV over dt equals 100
Perfect.
centimeters cubed.
dV over dt equals 100 centimeters cubed. Okay, so the change in volume is 100. All right. This here. All right, and this is something that the question is giving us, right? So we are given this. Okay. Next, we want to find something, right? So we want to find something. Let's see, it says, how fast is the radius of the balloon increasing? So what do we want to find in terms of derivatives? Oh, wow. Oh, no. Yes, it is DRDT. And once I get my thing back, we're interested in how fast the radius is increasing, which means I want to find what dr dt is. Okay, as we continue reading this question, it's asking us how fast the balloon is increasing when the diameter is 50 centimeters. So I want to find dr dt when the diameter is 50 centimeters. Okay, well, I'm interested in dr dt and it's telling me what the diameter is. Any ideas on how to change that question into maybe one symbol? Yeah, divide by 2. The diameter is just the radius times 2, right? So if I divide this by 2, this means that the radius is 50 centimeters. Okay. Oh, sorry, 25. Oop. Sorry about that. My typical algebra or arithmetic mistake every class. Okay, so that's pretty much all the question is giving us. It's giving us dv dt. We want to know dr dt at a specific point in time or a specific radius. Let's do step 4. Step 4 says to find an equation that relates our variables. Well, lucky for us, this question gives it to us and it says that volume is equal to 4/3 pi r cubed. So let's just write that down. Perfect. Okay. Step 5 says that we need to use implicit differentiation to find what we want to find. Okay. Implicit differentiation means we have to take the derivative of the left and the derivative of the right. What's the derivative of the left? Not quite. Oh, you're skipping ahead, but it is dv dt though, right? But nice job, John. The derivative of v is, well, 1 times dv dt. Okay, implicit differentiation is what we're doing here. Okay, on the right-hand side, we have 4/3 times pi, which are just variable, or not variables, they're constants, right? Just like regular numbers, pi is just like 2 or 3 or anything else. What's the derivative of r cubed with respect to t, Sam?
3r squared times the r over dt.
Perfect, using implicit differentiation with respect to t. Okay. Once we're here, we can clean things up a bit. We have dv over dt equals Looks like the threes will cross out, right? So we have 4 pi r squared dr dt. Okay. Now what we want to find dr dt. So maybe we should get dr dt by itself. Okay, so I'm looking for this. How do I get dr dt by itself? Yeah, divide 4 pi r squared on both sides. Oh gosh. So on the left-hand side, it looks like I have 1 over 4 pi r squared dv dt equals dr over dt, which is what I want to find. Okay, so I solved my equation for what I wanted. Let's go to step 6. Okay, step 6 says I need to plug in what I'm given and like what I want to find. Okay, so let's look at what we're given. We want to plug in dv dt, right? So we're going to plug in from step 3, dv over dt is 100 centimeters cubed. And since I found the derivative, I actually want to find the derivative at r equals 25 centimeters. Okay, so I'm also going to plug in r equals 25 centimeters. Okay. When we plug things in, oh, I didn't write, this is per second, sorry. I need to use centimeters cubed per second, sorry. Okay, when I plug things in, we're also going to plug in the units, okay? And the units kind of cancel themselves out. They work just like numbers when we square them or divide. Let's see how this works out. We have 1 over 4 pi 25 centimeters squared. dv dt is 100 centimeters cubed per second. Okay. Well, before we do this, maybe we should square the 25. When I square the 25, the centimeters also become centimeters squared. Okay, so it works just like a variable does. 1 over 4 pi times, what's 25 squared? 625, good. And this becomes centimeters squared. Okay. Okay. Once we get here, we can multiply together all the different numbers. And I think this gives us 1 over 25 pi. Okay. What are my units going to be?
Centimeters per second.
Centimeters per second, right? Because the centimeters squared and 2 of those centimeters and the centimeters cubed cancel out. And we're left with centimeters per second. Okay, so in total, the radius of my balloon is increasing at 1 over 25 pi centimeters per second. Any questions on what I've done here? Okay, these questions seem really hard because they're word problems, of course, but I think if you follow the step-by-step guide, you can really be able to solve these in an organized way. And the steps kind of do end up repeating themselves. Okay. One thing I want to say, or one thing I want to talk about is in step 6, I plugged in my numbers. Okay. Make sure with related rate questions, make sure you plug in your numbers at the very end. Okay. Don't plug in numbers in the beginning, always at the end, because if you don't, you might end up risking communicating something a little bit different than what you want. Okay. All right, that's my one warning to you. If you flip over to the next page, we have another type of question. I feel pretty confident that you guys can do this one on your own. I'm going to give you a few minutes to work on this, and just to keep things consistent, for notation, I want you to use X. Use X as your edge length. Okay, so that all our notes look the same. I do see some good answers as I'm walking around, but I kind of want to go through this using my steps. I know you don't have to follow my step-by-step way, but I like doing it just to organize myself so I don't mess up. So I'm actually going to do this one in front of the class, if that's okay. Okay, so we have 6 steps. The first one is to draw a picture, right? So step 1. Okay, the first thing we're going to do is draw a cube, right? Now, I don't know if my drawing skills are that great, but I don't want to draw maybe something like this. Okay. Something like that. That's a very bad cube, but I think that gives about a good idea of what's going on. Okay. So let's say that the length of an edge of a cube is increasing at a rate of 4 centimeters per second. So I guess the edge of our cube is going to be one of the edges, and we already said that we were going to label that as x. Okay. Now a cube, the edges of all the sides of a cube are the same, so it doesn't really matter which edge I label. But we know that the edge of a cube is increasing by 4 centimeters per second. Okay, we want to know how fast the volume of the cube is increasing when the edge length, or x, is 15 centimeters. Okay, so I think that gives enough for my diagram. Step 2, I kind of already gave to you. I told you to use x for edge length, so we're all using the same notation during class at least. But x is the edge length. And since we're looking at the volume, maybe we should use V. I think everyone used that for their example. Okay, so I labeled all the variables I'm going to use. Step 3 says we need to figure out what the question's asking and giving us, and we need to figure out what we want to find. Okay, so in the question, what is the question giving us in terms of derivatives?
dx of dt equals 4 centimeters.
Good, you're saying dx over dt is equal to 4 centimeters per second. And Jude found that out by reading the first sentence. It says, the length of an edge is increasing at a rate of 4. So the difference, or the change in x, or our edge length, is 4 centimeters per second. Everyone good on that? Good. Okay, now we need to figure out what we want to find. Oh gosh, I did not. Okay, we'll just keep it like that. We want to find something. What do we want to find here in terms of derivatives?
dv over dt.
Yeah, we want to find how fast the volume's changing, or dv over dt. And more specifically, we want to find how fast the volume is changing when the edge length is 15 centimeters. So when the edge length, or x, is 15 centimeters. Okay, so we have what we're given, we have what we want to find. Let's actually figure out how we can relate these together. Okay, step 4. Step 4 says we need an equation that can represent this. I have an equation in the question, but it doesn't relate v and x together. Can someone tell me how I can change that equation in terms of v and x? I know Zach has it.
X cubed.
Yeah, v equals edge length, or x cubed. Okay, so I know that the question says it in a weird way, but you can just change edge length, not egg length, into x cubed. Okay. So once we're here, we can do step 5, which tells us to take the derivative of both sides. What's the derivative of v? dv over dt. What's the derivative of 3x?
3x squared.
Great. Okay, it looks like we want to find dv dt, and we don't actually have to solve for it because dv dt is by itself. So we actually have everything in the form that we need. Okay, so step 6 tells us all we have to do is plug in what we know. So we're going to plug in dx over dt equals 4 centimeters per second. We're also going to plug in what we know, or what we're interested in, which is x equals 15 centimeters. Remember, plugging in always goes in at the end of these sort of problems. Okay, so plugging in, we have dv dt equals 3 times x cubed, so 15 centimeters, or sorry, squared, times dx dt, which is 4, centimeters per second. Okay. What's 15 centimeters cubed? I got something different. Is it 175? It might, I got, did someone say 225? Okay, I got 225, but no, that's an Amy mistake. And what's the units after I square 15 centimeters squared? Centimeters squared, good. Okay, this is still multiplied by 4 centimeters per second. Multiplying everything together, I got 2,700. Okay, what are my units going to be? Centimeters cubed per second. Just treat the units like variables and you'll get what you want. And that's my final answer. So it looks like my cube, the volume of the cube is increasing at a rate of 2,700 centimeters cubed per second.